Good afternoon, everybody, again. I will present today the work which has been mainly realized by Zhichao Y, a colleague of mine. He has been working on his PhD on this topic. I will talk about biaxial bicyclic experiments, but we are still staying with ductile damage. Means we are doing very low amount of cycles here. The talk will contain modeling parts, material modeling parts. It will contain simulation parts, but I will focus on the experimental part because that is where I gave my biggest input here. Let's start. Ductile damage is known to be stress state dependent. If you have stress triaxialities, maybe around 1/3, like in a tension test, you get rather void-dominated damage mechanisms, or if you have a shear test, like indicated here, you get the smearing of the pores, and you have like more in the ZEM image, some aspects like shown here. So the continuum damage model is proposed as follows. Depending on the stress triaxiality, you have for high stress triaxialities, you have formation of voids and growth of voids and nucleation later on. For low negative stress triaxialities below a certain cutoff value, you have no damage. And then you have micro shear cracks, means smearing of the voids for triaxialities around 0, and you have an intermediate zone. So important to point out, damage as well as also plasticity is known to be stress state dependent. So another aspect about damage and also plasticity and these subjects is that these processes are load path dependent. Here we see results of a monotonic tension test and of a cyclic tension test. And even here, you see small differences in the images. This becomes more significant if we are looking at difference, or if we are changing in between different stress states. And that will be focus of the next slides. So we have damage is stress state dependent, damage is load path dependent, and the third aspect would be that damage is depending on the material direction or on the material orientation. But this aspect is not taken into account here. We have been realized all these experiments with aluminum 6082, which is almost isotropic. So no material orientation dependence here recognized. The phenomenological model works as follows. We have a certain elastic region and fulfilling a yield condition. After fulfilling the yield condition, we have elastic plastic material behavior. And then in the same or in a similar way, a damage condition is introduced. And in continuation here, we have elastic plastic damage material behavior. Final phasure occurs with the macro crack. So we have cracking, which is not studied here in detail. This is still ongoing research. So this is the basic idea of the material model. So we have several aspects here. We have the strength differential effect, means different behavior here. We have the Bauschinger effect. We have non-hardening effect. This is recognized in the continuum damage model. Here a slide regarding the plastic behavior. And I want to point out just very on the bottom here, and that is what Zhichao introduced and he added to the continuum damage model. We have combined hardening, which is kinematic and isotropic hardening. So this was added here, and this is contained in the simulations or in the results of the simulations. We have a Docker-Paga yield condition. So we have a yield condition to limit the elastic area, and we have the plastic flow rule. In a similar way, we have a damage criterion, and we have a damage evolution equation. So this will cause damage strains. And that is an aspect I gave him an idea to Zhichao, and he took it, because how does this damage surface change with ongoing loading? Probably it's a very difficult subject. This is, you have to do experiments, but it's very difficult to do, because you are way in the plastic region, and then you want to find out something about damage, which is very difficult experimentally to detect. So, but at least here we were able to add this, and he did it in the same way or in a similar way than plasticity was doing, combined softening. Okay, a few slides about experiments, specimen geometries. Here we have the uniaxial loaded specimens. This is where he started out with, or we started out with. And we shortened this tension specimen to a very short region. And then we aligned our testing machine very, very good. Means we had to repair it for 6,000 euros. And so, so we could do with the same machine tension and compression experiments to find out about the difference in that behavior. So very short, very compact region here. Then we did shear experiments. We have this double notched shear specimen. I personally prefer 2 shear regions, because you can avoid rotations of these parts. And in numerical simulations, you avoid problems with boundary conditions. Because if you have just one shear region, they rotate, and it doesn't matter really if you clamp it or if you just have a bolt there. These tend to rotate. So this is why we prefer these double notched part. So the idea is to have shear stresses here in this region. Having a look at biaxial spacements, this is the H, or is a modified H spaceman we call HC, H for the shape we have here, and C for cyclic. This was modified. We have a bigger gap here to allow cyclic loading also in this shear axis. The main idea of this specimen is that you can load this axis, like indicated up here, and you get, depending on the loading direction, you get tension or compression loading here. And if you load this axis 1, you get shear stresses in the notches. So you can superimpose tension with shear or compression with shear, and you can change during the experiment. So you can really do a lot of different loading passes with this geometry. The first idea when I designed this about 10 years ago was to have a more or less direct relation in between loading and stress state here in the notched area. Sure, you have gradients here, but it's unavoidable. Almost every geometry has gradients. The setup, experimental setup, biaxial testing. We have here a view on the biaxial machine. Here we see this big fat part in the middle. That is a new downholder we have, like 2 years ago, we bought or we designed in cooperation with Walter and Bai. and it reduces the possibility or the danger of buckling. If you want to do compression in both axes, you have buckling or you have problems with buckling. We can do compression in both axes till a certain point. But if we do tension compression, we can do that. I will come back to that issue later on when I show results from this. How to call these experiments? First, we started out with monotonic loading, means we are loading both axes simultaneously monotonically, causing a stress state here in these notches and plastic and damage behavior occurrence there. Then we have single cyclic loading here in the middle. The idea is we load one axis, in this case here, the tension axis, we load it till a certain limit, and then we do cyclic loading in the other axis. Another one is we load the shear axis till a certain point, till a certain load, and then we do cyclic loading in the other axis. And then we started out doing bicyclic experiments. Means we're doing simultaneously loading cyclic in both axes. And as you can imagine, having a look at these experiments in this way, you have a very rich possibility to come to different stress states and change these stress states. Mean you can do the loading or the load path dependence. You can focus on that. Okay, let's have a look at some results. Here we have single cyclic shear, means here the red mark, you load till a certain limit, and then you start doing cyclic loading here. And if you can see here, we load first till a certain limit in tension, and then we start loading just here. And as you can see, you have big differences in the maximum displacement you can reach in this axis. One other idea about these experiments is that we defined the number of cycles. Here in this case, 1.5 cycle, and then we load it to fracture. You can also do cycles till it fractures. That is what we are currently working on. Single cyclic tensile. This experiment is a lot more difficult to realize due to the fact that if you load till you have plastic deformation here, it's very difficult, or if you load till you have plastic deformation or significant plastic deformation in shear axis, it's very difficult to do cycles to the plastic regime in tension axis, because you can apply a lot less displacement in tension direction. Bicyclic experiments here, you can see here the TTT stands for tension, tension, tension. This is not bicyclic reverse already. It's still because due to the fact that this tension axis is not loaded to compression. This axis just goes up, down to 0 and in tension again. This is this tension axis. While the other axis does shear in one direction and reverse loading till here. So here you can see the principal strain. You have at the reverse point 1, means somewhere here. Then you have reverse point 2 somewhere here. you see that the direction of the shear band changes. And then you have at fracture point still this here, but it's not so good visible because of different scale. And this is the strains you get before fracture. And again, here you see the accumulated damage strains we predict. Here we have bicyclic reverse experiments. Means the second axis is also coming to compression. And this is the point I wanted to come back to. 1 minute? Yeah. 1 minute? Okay. This is a critical point in this experiment because we are coming to both compression loading, which might cause buckling. And this is limiting this experiment. Okay. Some ZAM images to the second, and you can see clear differences. And then we have some key takeaways. We have some outlook. And we have some literature. And thank you for your attention.